Okay, last week, not last week. In the last class, we talked about likelihood ratio and a multivariate likelihood ratio and how maximum likelihood estimation mechanism works, right? And then a couple of the different statistical tests use likelihood. So first, we talked about the WAL test, right? The WAL test use a maximum likelihood estimate to conduct hypothesis testing. Then second, we'll talk about the likelihood ratio test. Sometimes it is called the deviance test. Okay, so likelihood ratio test is very commonly used in any statistical analysis or any psychometric analysis. Okay, so likelihood ratio test is a very common alternative to WAL test. So it compares likelihood values between models. So likelihood ratio test is very commonly used to compare multiple models. You can develop multiple models based on your hypothesis. Okay, I want to add this path. I want to add this path. You can compare, and then you can decide which model works best, right? The fits better. And in that case, you can use the likelihood ratio. The likelihood ratio test compares the likelihood values between the full model and restricted model. So sometimes it is called null model. Sometimes it is called alternative model. Okay, they're same. So in this situation, so in our previous example, we try to predict job performance using cognitive ability, right? So the regression includes only if your regression model includes any predictor variable, that could be your full model, and then contains no regression slope, that will be alternative model. I'm sorry, that is null model or restricted model in this case. For example, job performance is beta 0 plus beta 1 cognitive ability. This is our main model, right? So let me say this is a full model. And then our restricted model will be only intercept. So there is no predictor here. This is a restricted model, right? Then we can run each model and then get the likelihood values from the restricted model and then full model. And they get the difference between these two models, so likelihood, and then -2, right? If you put the -2 and log likelihood, that is what? That is deviance, right? So deviance is a measure of misfit. Okay, and likelihood is a measure of fit. So in that we test this likelihood ratio using the chi-square distribution, because the likelihood ratio, statistically, likelihood ratio follows chi-square distribution. Right, so here are some steps. So first, we estimate the null model, right? So for example, job performance equals inter intercept and then no predictor. So this is our null model, and then you can get the -2 times log likelihood value, and then you can estimate alternative model. Now job performance is beta 0 plus beta 1 times cognitive ability. Run it and then get the -2 times log likelihood value deviance, and then get the difference between two deviance. Compute this one. This is 14.4 in our example. And then, I'm sorry. So this is, what is that? I think that there's some missing here. Is it correct? Is it right? 14.4. What? So test. Okay, let me. I think that there is some mistake here, so I will fix that. Let's look at the our code. So first, I downloaded my example file here, and here is the data set, right? IQ score and job performance, right? And then I'm using N, uh, NLME package. So this is not linear, generalized linear model package. Install it. And then I'm running a regression model. So this is, let's run this model first. Empty model, right? So there is no predictor. So this, I just put 1. So which means I'm going to estimate only intercept. Okay, there is no predictor. So, and then our data file, data set is data. And then I'm going to use ML estimation. So, and then GLM, decision function. And then if you get the summary right here. So this is our model, not model. And then AIC, BIC, we'll talk about this one later. And this is log likelihood value, minus 40, minus 47.58. And then here coefficient, this is our intercept, right? And then these are standardized residual information. And then now let's run a full model. So I just named the full model, the GLS function. Job performance is dependent variable, IQ is independent variable data set. And then this is our multi ML method. And then now we got, so this is our model, AIC, BIC, and then this is log likelihood value, right? And then this is the intercept, this is IQ slope, right? And then residual values and this one. And then, so you can get the log likelihood value of restricted model and full model, right? So the full model, log likelihood value of the full model is this one. But you can just copy, you can copy and paste here like this. But I just use some code. So if you like structure, if you look at the structure of this full model, so you can see here, right? Log likelihood value. So you can use this one. So in that way, you don't need to copy and paste all the values. Okay. So I just copy and log likelihood. This means, okay, I'm going to extract log likelihood value from the full model. And this is log likelihood value from the restricted model. Okay. Get the difference and -2. And then I save the result as a D. Run it and check. Okay. So this is -2 times log likelihood value difference. 6 times 99. And then this log likelihood, the difference and ratio, this follows a chi-square distribution. So I tested using chi-square distribution, P chi-square, and then this is this distance, a difference value. And then degrees of freedom, difference is only 1, because if you look at this model, this is the summary model, degrees of freedom is, where is degrees of freedom? 20, what, 20? Okay. So right. Degree of freedom. 20 total, 18 age. Okay, so right. So degrees of freedom difference is only 1, right? Because we have only one the parameter difference between these two models, right? So we added one slope. The full model has a slope, but alternative, I'm sorry, full model has a slope, but restricted model has no slope. So we have a one parameter difference. So the degrees of freedom should be 1. Okay, do you follow me? So, and then this is a chi-square distribution test. So, okay, we're gonna use the right side tail because chi-square distribution is a one tail test, right? So it is false. If you specify false, that means we are going to use upper tail. So if you run it, okay, so there's some warning message, but we can ignore this one. So this is less than 0.05. It's a significant, right? So what does that mean? So here is the significant result. So we reject our null hypothesis because our null hypothesis is null model fits better. That's our null hypothesis. So we reject it. That means our alternative model or our full model fits better. So the regression slope for IQ was significantly different 0. Okay, so this is our interpretation. IQ significantly predicts performance. So our alternative model fits better than our null model, right? So this is likelihood ratio test. But the good news is you don't need to go through all this step because R provides this function, ANOVA function, right? If you just run ANOVA right here, ANOVA, and then you can put the restricted model and full model and just run it, repeat, it gives you a result. And right here. So where is it? So this is restricted model, full model, and then test 1 versus 2, a log likelihood value difference, and then it computes likelihood ratio, and then p-value. So this is what you need. P is less than 0.05, right? So we reject null hypothesis. So that means our full model fits better than restricted model. Okay. So in the real analysis, so you can just use ANOVA. But sometimes you may need this process for the advanced measurement model. But in most statistical analysis, you can use ANOVA to the likelihood ratio test. Okay. And now information criteria. So information criteria is another statistics to determine the relative fit of your model. Okay, but a VAR test and likelihood ratio test, they are used for the comparison for nested models. But AIC, BIC, or SABIC, and a couple of more. These information criteria are used for non-nested model. Okay, what is a nested model and non-nested model? So for example, y equals 1 plus 2x and y equals 1 plus 2x, and let's say b0, b1, b0, and b1 plus b2, x2. So look at these two equations, regression lines. So it means the first regression model is nested within the second regression model, right? So this part is nested in this model. Right? So in this case, this is called nested model. But not nested model, it's like y equals x2, y equals some square root x. Okay, they have a totally different distribution with different model. Nothing nested here. So in this case, that is not nested model. Okay, so the AIC, BIC, SABIC, they are used for non-nested model. But the important thing is AIC, BIC, or SABIC, and many more, they all used the deviance information. Deviance is minus 2 times log likelihood, right? So deviance is measure of misfit. So do we want smaller number or larger number?
Smaller.
Smaller number, right?
Yeah.
So that's why AIC, BIC, SABIC, the best model is one with the smallest number. Okay. When you interpret the AIC, BIC, SABIC, you need to find the smallest number. And then the model having smallest number is the best model. Okay. This because these information criteria all includes the deviance part. So please don't use information criteria for nested model. So for the nested model, the likelihood ratio test are more powerful, or wild test. And then also many different types of there are many different types of information criteria. Here is the R only provides AIC and BIC, and but M plus program and other program also provides SABIC. This is the sample adjusted BIC. Based on the simulation study, so SABIC, the performance of SABIC is the best, and then BIC is the second, and AIC is the last. Okay, but this is a general rule of thumb. But when you report your result, you have to report all of them. And then they don't agree. They don't always agree each other. Sometimes you have, okay, model A has a smaller AIC, but model B has a smaller BIC, but model A has a smaller SABIC. Sometimes you may have some conflict results, okay, among these information criteria. So what should we do? In that case, you may more rely on the BIC or SABIC results. Okay. And we will use AIC and BIC statistics for the latent class analysis and latent profile analysis later. So these statistics will be used.
So I have a question.
Sure.
So for your nested example, your equations, what if there are a few cases in, let's say B2, X2 that have missing data and your number of cases aren't equivalent? Is that considered a non-nested model?
No. No. So nested model, non-nested model is only for the model parameter.
Okay.
Not people. Okay. So this equation is quite. Did you guys learn about the CFA model? Or did you take the psychometrics? Oh, some are yes, some are not. Okay. So for example, you know, okay, I will not talk about that. So because some of you didn't take psychometrics yet. Okay, this is information criteria. So which test should I use, right? So we have a WAR test or likelihood test. So the answer to this question depends on the sample size and the parameters that you are testing, okay? So the likelihood ratio makes no assumption about the shape of the sampling distribution. So it is generally superior to the WAR test in small sample size, because sampling distributions eventually normalize as the sample size gets very large, but they can be markedly not normal in small sample size, right? So this is a problem for the WARD test, because WARD test uses the normal distribution to generate the probability values. So In other words, VAR test assumes normality assumption, but likelihood ratio test does not have that assumption. Okay, so it is generally superior to the VAR test in a small sample size. But if you have a large sample size or moderate sample size, doesn't matter. Okay, so for small sample size, it's better to use a likelihood ratio test. And there are practical considerations to examine when choosing between a VAR test and likelihood rest test. The first, so VAR tests are easy to implement, right? Because the most software just provides t-value and p-value. You don't need to do another analysis, right? You don't need to compare two different models. The VAR test just run with the one model, single model. But the likelihood rest test is somewhat less convenient because it requires two different models. You have to compare two different models, right? But you can still use ANOVA function in R, right? So it's easy. So that's one thing. The second, the VAR test is not invariant to change in model parameterization, but the likelihood statistics is invariant to model parameterizations. So its value is unaffected by the choice of a model specification. So what the hell does that mean, right? So this you guys already, some of you already took psychometrics. Think about the conformity factor analysis, right? There are two different parameterization strategy. You can fix factor loading at 1, right? Or you can fix factor variance at 1. So both methods, both approach, model identification approach gives you the same result, same model fit, right? But if you try to different parameterization, and VAR test will give you the different result. But likelihood ratio test is invariant to the model specification parameterization issue. Okay, that's another difference. Okay, so I know this is a little bit advanced, but likelihood ratio test is invariant to the model parameterization. Okay, if you don't understand what I'm saying right now, it's okay. Okay, but because it requires just some knowledge about the psychometrics. Okay, but if you already took a psychometric, you should understand what I'm saying. Okay, right, the summary. So first, the goal of maximum likelihood estimation is to identify the population parameters that have highest probability of producing the sample data. The sampled log likelihood quantifies the fit between data and then primary estimates, right? And provides a basis for choosing among a set of plausible primary values. And for the multivariate data, each unique combination of primary estimates is the best different log likelihood value. So for multivariate data, if you have 4 variables, you will have a 4-dimension multivariate normal distribution, right? If a 10 variable, you will have a 10-dimension, 20 variable. And then maximum likelihood estimation is trying to find the best set of parameters to make the highest maximum likelihood value. Okay. And the first derivatives of log likelihood function produce the maximum likelihood estimate, right? So in that way, we don't need to do all the grid search approach. And then the univariate VAR test is the ratio of a point estimate to each standard error. So beta divided by square root of a standard error, right? So that is the univariate VAR test. But multivariate VAR test is very similar to the univariate counterpart, but it uses matrices and covariances. And the likelihood ratio test, I'm sorry, it should be a ratio, not a ration. Ratio test, the difference between log likelihood values from the two models provides the basis for the significance test. And then information criteria, they uses deviance minus 2 times log likelihood. So the smaller values is always the better fit. Okay, any questions? No? You're all clear? Okay, so let's talk about missing data. Right. Okay, let's talk about missing data. I don't like missing. Nobody likes missing data, right? So, but we always have a missing data in the real data set. So when I was young, so every time I went to school, I missed something. So I came back home. My mom always said to me, "What are you missing? What are you missing?" So I don't like missing, but so missing is all, and it's data is always having some missing variable, right? You would never get a complete case of a data set. So there are many different regions to have a missing data, right? So it could be totally random, or it could be systematic, or it could be a random choice, or some careless responding, or so, and especially in the longitudinal data analysis that you may find a lot of missing data, right? So how can we deal with that? So I will use this example data set for this missing data example. So to demonstrate some of the ideas of the types of missing data, let's consider a situation where you have collected two variables. So first one is IQ scores, and second one is the job performance. So this is a job performance complete scores, and our sample is 20. Okay, it's a very simple data case. Then imagine you are an employer looking to hire employee for a job where IQ is important and cognitive ability is important. Okay, so this is 20 samples and IQ and complete data set. We have complete. And then there are three different types of missing. Okay, so the first one is missing completely at random, so which is called MCAR, and missing at random, MAR. And the last one is the missing not at random. Okay, so these are there are three different types of missing case. So let's talk about the missing completely at random first. So missing complete at random is just like this is completely at random. It is like a flip the coin. Okay, the flip, if you flip a coin, it's a 50%, 50%, right? It's totally random, right? So random missing data occurs totally random. It's a purely haphazard missing. Okay. So the formal definition of MCAR, missing completely at random, requires the probability of missing data on the variable y is unrelated to other measured variable. Okay. So your missing is not related to other variable. And also your missing is not related to the variable itself. So this is, if you look at, this is our complete case, complete job performance. And then we randomly remove some numbers, okay? I just randomly remove some numbers. And then this is MCAR type, the missing completely random type, the missing data, okay? They are all randomly removed, okay? So MCAR is more, this is pretty, it has a pretty strict assumption than other cases of missing, because it assumes that the missingness is completely unrelated to the data, right? So, but in the real world, in the data, it rarely happens, because some missing could be influenced by other missing, right? So this assumes very strict cases. So all the missings is completely random and independent in the other cases. So for example, in our missing case, let's say M is missing, and M is missing. Missing are statistically independent of our observed data. So we are, this is our job performance and this is IQ values, okay? And this is our M. Let's say this is missing, okay? And this missing is influenced by some external factor, some third factor, okay? But we don't know what that is. So this is more hypothetical factors. But the important thing is there is no relationship between these two. Our missing is not influenced by the IQ score or job performance score. Okay. So this is missing completely at random case. Any questions here? No, you're good. Okay, so look at this. If our data set is missing completely at random, and then IQ means will be, this is our complete data set, and that IQ score is 100.80, right? And then only complete cases. So that means removing these missing, after removing these missing, and then mean IQ of complete case is 99.73. So what do you think? They're very close, right? So what I did is I just removed missing cases. So this is called list-wise deletion. We'll talk about it later. So the deletion approach works fine if the data follows the MCAR assumption. Okay, if your data is completely at random, in that case, you can remove the missing data. You will still get the unbiased estimate of your parameters, the population parameter. Okay, so but implication of MCAR, so because the mechanism of missing is not due to anything other than chance, which means it is a totally random. So inclusion of MCAR in data will not bias your results. Okay, because it's totally random. So you can use methods based on list-wise deletion or pair-wise deletion, and we'll learn about this one, multiple imputation or maximum likelihood estimation. Okay. But if list-wise deletion used, if you use list-wise deletion, that means your data should be missing completely at random. If your data is not missing completely at random, in that case, your deletion caused some biased results. Okay. So if list-wise deletion used, so your effective sample size will be lowered, right? Because you removed it. And the less power and less efficient. And the standard error will be larger. And also, if you X1, X2, X3, and X4, and X5, and 1, 2, 3, 4, 5, right? So this is missing, and this is missing. And if you remove all of them, you will lose other information, right? These are all the important information, but you will lose it, right? And this hypothesis test of MCAR to exist for in the statistics. So some people use univariate t-test. So you just you compute the mean difference between with missing and without missing. Okay, and then if there is no significant differences between these two, and they just assume your missing data is MCAR, missing completely at random. And the Little's MCAR test, this is another test, but this is beyond our scope, so I will not talk about this one. So under MCAR, so pretty much anything you do with your data will give you the unbiased estimate of your model parameters. As long as your data, missing data is missing completely at random, in that case, you can use any techniques for missing data. Okay. But it, unfortunately, in real data, it rarely happens. Okay. So any question about the missing completely at random? No. Okay, now let's talk about the missing at random. So what is missing at random? So data are missing at random when the probability of missing data on variable y is related to some other measure, some other variable in the analysis model, but not to the values y itself. Okay, so in this case, this is our IQ score, this is our complete data set, and then as you can see, we have some missing values here, right? And let's say we set some cutoff score for selection purpose. Okay, so they have job performance, job performance, and then they're actually screened because of these IQ scores, right? So this missing is attributed to the IQ score, right? So probability of missing data on a variable job performance is related to the IQ score. This is missing at random, okay? So look at this. So data are missing at random. If the probability, right here, so this is IQ score, JP, job performance, and this is our missing, right? And hypothetically, so this missing will be related to some, unknown third factor. So this is hypothetical relationship, but important thing is here. So this missing is related to the third variable. Okay, so this is missing at random, MAR. So if we get the mean of these complete cases, so okay, let's get the mean. So this is our mean is 80, no, what is that? This one is 105.5, right? So, but if we get the incomplete cases, if we get this mean, that is 83.6. So I just did a list-wise deletion, right? So this list-wise deletion is biased estimate when data is not missing complete at random. Because this data type, missing data type is MAR, missing at random, not missing completely at random, right? But this is a more realistic case. So implications of MAR. So if data are missing at random, the biased results could occur. Okay, so inference based on list-wise deletion or pairwise deletion or mean imputation or median imputation, they will be all biased. Okay, so inference is, again, if your data missing is if it is not MCAR, your list-wise deletion or pairwise deletion, these are all the traditional missing imputation method, right? And mean imputation or median imputation, they will be all biased. Okay, but good news is a maximum likelihood estimation or multiple imputation. We'll talk about that later. This method will be unbiased. And for the MAR. So maximum likelihood estimation and multiple imputation, they are quite, they produce the unbiased estimator, either both MCAR and MAR situation. Okay. So MAR, missing at random, is the common compromise used in most empirical research. So under MAR, maximum likelihood algorithms or multiple imputation, so we will talk about it later, they produced unbiased estimator. Okay. Any questions? No. Okay, so missing not at random, this is worst case. The data missing not at random, which is called MNAR, MNAR, I don't know. So missing not at random. So data missing not at random when the probability of missing data on variable Y is related to the values of Y itself. Okay, the missing value is related to the variable itself. Okay, even after controlling for the variables. We have missing here, but actually these missing values are related to this job performance variable itself. Okay, this is missing not at random. Okay, so in this case, so our missing data, right? This is our missing data. Missing data is related from, we have some, the missing in IQ score, no, I'm sorry, job performance, right? So this missing is related to the job performance itself. And also this missing is can be related to another variable. Okay, but this relationship defines the missing not at random. But practically, it is almost impossible to identify the missing not at random because, so these variables are missing unless we ask them, each individual, why did you miss? Why did you miss this variable? I mean, unless we ask them, everyone, we don't know the true answer for that, right? So this is more like the hypothetical and theoretical typology, but in real world, we can't identify the McNAR, okay? So data, we talked about this. This is often called the non-ignorable missingness. So inference is based on list-wise deletion or even maximum likelihood estimation or multiple imputation. That will be all biased in this scenario. But in practice, it is impossible to know the data is really truly MNAR or not. So practical approach is to treat the missing data as MAR. missing at random. Okay, so implications of MAR, MNAR. So this is the worst case scenario when data are MNAR, missing not at random. So you cannot easily get out of this mess, right? And so it's almost impossible. But analysis algorithms must incorporate models with the missing data. There are very advanced models to deal with these types of data set, but that is beyond our scope our scope of this class. So, it is impossible to know definitely if data truly MNRs. So this is the practical approach. So data are treated as MAR or MCAR. Okay. So what is the safe strategy if you have any missing data? Probably the better approach is to treat your data as MAR, right? And then try maximum likelihood estimation or multiple imputation. Okay. Or there are a couple of more imputation method in machine learning. So maybe KNN imputation or decision tree back trees imputation, but they are based on the machine learning algorithm. So they also produced unbiased estimate to MCAR or MAR. Okay. So my suggestion is to use maximum likelihood estimation or multiple imputation to your missing data. Okay, summary. And traditional methods assumes MCAR mechanisms, right? What is a traditional methods? List-wise deletion, pairwise deletion, mean imputation, median imputation, mode imputation. They all assumes your missing data follows MCAR mechanisms, right? But if your missing data is not MCAR, it will yield biased parameter. Okay, so, and the second, but maximum likelihood estimation or multiple imputation yield unbiased parameter estimates with MCAR or MNAR data. MCAR or MAR. It sounds weird, but and however, these methods are not perfect, right? Because they cannot fix MNAR problem, right? But practically, it is impossible to identify MNAR, the data. So we just use maximum likelihood estimation or multiple imputation for missing data. Okay. Any questions? No question? Is it clear? Okay. All right. The second, some methods for dealing with the missing. So missing data can alter your analysis results, right, dramatically, depending on your type of missing data and the type of analysis algorithms, right? Let's say you collected the data for your dissertation and you found 20% are missing or unfortunately, 30% are missing. And then you want to get some significant validity evidence between two variables. And you just run correlation analysis. If you just run correlation analysis using SPSS, do you know what SPSS does for the missing, for correlation analysis?
Pairwise?
Yeah, right. Pairwise missing. So the correlation analysis, correlation will be based on the pairwise pairwise deletion. So you may have the different sample size. So X1 and X1, X2, X3, X2, X3, right? So X1 and X2, to get the correlation using only complete case between Xm and X2. And then you can get the correlation here. And then get the correlation using only complete case of X1 and X3. You will get another correlation. So your sample size could be different. So it could be 50 or it could be 70. Okay. So and then, all right, my correlation is 1.1 and this is a 0.15. And you expected a significant correlation. Unfortunately, you found a non-significant correlation. And maybe that means maybe you apply the wrong techniques, right, to deal with the missing data. Because if your data is not MCAR, but realistically, it could be more MAR, right? So this analysis will be severely biased. It will affect your dissertation results. Okay. So the choice of algorithm and missing data method is very important in avoiding issues due to the missing data. Okay, so first, this is a deletion methods. List-wise deletion and pair-wise deletion. The list-wise deletion, you just delete entire observation if any values are missing. Right? You just remove them. And a pair-wise deletion is a delete a pair of observation if either of the values are missing. So x1, x2, x3. Let's say this is, we have some 10, 11, 12 missing, 13, 14, and missing 11, 12, not 10, 14, 15, 16, 17, and 9, 7, 8, 7 missing, and 10, okay? No, I'm sorry, so let's say we get the missing, okay? So pairwise deletion is when you get the correlation, you just use the complete cases. This is missing, right? You will not use this one. This is missing. You will not use this one. So you will get the correlation using only 4 cases. Okay. And then this is correlation x1 and x2. So this correlation is based on n equals 4 because we use only complete cases in this case, right? What about this case? y2 and y3 correlation x2 and x3. This is x is missing, so we are not using this one. And this is missing, and this is missing, right? So 3 cases are removed, and we are using this one, and this one. So this correlation is based on these 3 cases. Okay, so this is a pairwise deletion. This is typical correlation, the methods to deal with missing data. So you may have different sample sizes for each correlation. Okay, that is pairwise deletion. But these methods assumes your data follows MCAR assumption. So definitely it will produce the biased estimate if MCAR or if your data is MCAR or MNAR. I'm sorry, MAR or MNAR, right? Also, you remove the data point, so it will affect your power, right? So in the list-wise deletion, just talked about that, right? We discard all of the data from the observation, right? So, and this is most frequently used in statistical software packages that are not optimizing a likelihood function. So in undergrad, the research method class, okay, if you have any missing data, delete it. But that's the worst, the technique to deal with the missing. And pairwise deletion, I just talked about that. The pairwise deletion discards a pair of observation if either one is missing, right? So it also assumes MCAR, right? So definitely it will is a biased estimate if your data is MAR or MNAR, right? Okay, and then it can be an issue when forming a covariance and a correlation matrices, because if you want to do some advanced statistical method, so your correlation and covariance matrices will not be identified because you have a different n size. Okay, so it is some problem. It is a limitation. Okay, so now I'm going to show you missing data in R. Okay, so first I'm going to install the VIM package and the mice package. These packages are for the multiple imputation and missing data analysis. The both are very useful. So first you need to install it. And then I'm going to import my data. So the missing type data. So right here. So this is the same data set, right? So we have IQ score 20, and this is a complete case 20, and this is the MCAR data, and MAR and MNAR. Okay, and then we'll see. Then I will show you this is how to identify your missing data. So I just created a vector and then I put NA. NA means missing. Okay, and then I saved here. And then if you run it, and then you can use isNA function. So isNA, the vector has any missing values, and the first element is not missing, so it's false. The second element false. Third element is false. The last one is true, right? So this is NA. Okay, and then list. The row do not have a missing values, so you can get the complete cases from you can get complete cases using complete.cases function. Okay, if you run this one, it will return all the false and true or false the logical operator values. Okay, so the first element is not missing, second element is not missing, third case is not missing, and true. This is true, true, true. So it will return the only true cases. So the missing, so if you run it, it's okay. Now you can get the complete cases. So 1 to 6 were gone, right? We have only 7, 8, 9, and 10 so deleted, 11 deleted, and 12, 13, 14, 15, 16, 19, and 20 deleted, right? So you can use complete.cases function. Also, if you put explanation, that means it's opposite, okay? So you want only missing cases in this case. Complete cases. If your data set is not complete, if that is true, please return. Okay, so run it. And now you have all the missing cases here, right? So this is missing. And then now you can check the missing pattern using the md.pattern function. So if you run it, it's too small. It says it's too small. So Okay, now we get this result. Okay. So let's go back to my slide. Okay. If you run this one, if you md.pattern, you can evaluate the patterns of your missing. So this means, okay, IQ score. We have IQ score and job performance, complete data, and MCAR, MAR, MAR, right? So the 10 cases, this is cases, has no missing. This is missing. This is cases. And 2 cases has 1 missing, and that missing occurs here. Okay, and 1 case has 1 missing, and that missing occurs here. And the same thing, 2 cases have a missing, 2 missing, and that missing occurs here. So in that way, you can evaluate the missing. And then also these values returns missing values for each variable. Okay, so IQ, they're all complete. So there is no missing, right? Complete cases, no missing. And MCAR, the variable, we had a 5 missing, and 5 missing, 5 missing. This is total missing. Okay. Oh, I'm sorry. Do you follow me? Okay. So, and then it gives you the graphical presentation for here. It's the same. So this is cases. These are missing information. Okay. So 10 cases has no missing. Okay. They're all complete cases. Blue is complete. Red is missing. It's not, I think it's a purple or something, red. So, okay. So 2 cases has only 1 missing, and the missing occurs here. Another 1 missing here, and 2 cases had 2 missing right here, right? In the same way, we can evaluate this one, and that these values are all missing information of for each variable. And this is total missing. This is MD pattern function. Question? Okay. And then also you can evaluate more advanced patterns using, we already installed this package, so using AGG aggregate function. Okay. So first you have to specify your data, and then numbers true. This means it will return the frequency or proportion as numeric information. Okay. And then sort variable. So if you specify it as true, it will sort by descending order. Okay. And then I added the labels, my graph. So proportion of a missingness and missingness patterns. So it will give you this result, the first. So MCAR and then 0.25. This is not a frequency. This is a proportion information. Okay, so 25% of the MCAR data is missing. And MAR is another 25%. This is another 25%, and these are 0%. They are all complete cases, right? And then also it produced a graphical presentation, so it's much easier to read, right? 25%. So MCAR, MAR, MNAR, they all have 25% missing. And then IQ, and this one has no missing. And then last. And then missing pattern, this is another graph. So these numbers are proportion. Okay, this is a proportion. So 50% of your data has no missing, right? No missing. And 10% of your data has a missing, but missing occurs here, MNAR. Okay, and 10% of your data had a 2 missing. That pattern is it occurred MAR or MNAR. Okay, and also the 5%, 0.05% of your data had a missing, and that occurs here and here. That means it occurs MCAR and MNAR variable in this case. So in this example, I used MCAR, MNAR, and this one, but maybe in real data. So this is a variable. Well, for example, this is job satisfaction and work family conflict and IQ, and what is this? Some, so some different variables. Okay. This is how you can evaluate the patterns of missing. Any questions? Is that clear? Okay, so now I created 3 separate data the frame. Okay, so and actually 4. Okay, this is only for complete cases. And then from the missing data, all row and the first and third column is for MCAR. Right. For here. Okay, this is IQ and MCAR. I created 3 different data set because I'm going to use for another analysis. Okay, so this is what I did. Okay, from the complete data set, I created a new 3 data set here. And then you can check your amount of your missing data using the ease.na. Okay, so and then if you run this one, it will give you this number, true or false, right? And true or false, this operator can be either stored as a numeric value 0 and 1. Okay, so if you sum that, you will get the missing value of a car variable. Okay, that is 5. Okay, 5 cases are missing. And then also you can get if you compute the mean, that will be proportion because this is 0 and 1, right? So if you compute, okay, 25% are missing. And then what about the not missing case? So using total data set, so run it, okay, 50%. So 50% are not missing, okay? And that way you can easily check your amount of your missing data, okay? So I think I will stop here and we'll keep talking about the missing data analysis. The next class. So, you already know the list-wise deletion, pairwise deletion, the mean imputation, and other cases, but multiple imputation is a little bit complicated. Okay, it's somewhat complicated. So, so it might be some confusing, but I will explain it as easy as possible in the next class. Okay, sounds good. Any questions?
Phil, I have a quick question.
Sure.
There you have a longitudinal data, you want to do missing data pattern. Do you treat each time point as a separate one or just give them overall picture?
If you have a missing in the longitudinal
right,
data.
You say you have 3 time points and then some data is missing at time point 1, some is missing time point 2. Do I treat Like, do I look at time 1 first and assess the missing pattern, and look at time 2 and missing pattern, or just look at the overall 3 time point of the missing pattern across?
That's a great question. Based on, I'm not very familiar with the longitudinal analysis, but based on my understanding, so full information maximum likelihood estimation is the best way to estimate the longitudinal missing. So the FIML, which is called the FIML, full information maximum likelihood estimation, is estimate the parameters based on the each cases, each time point.
Okay.
So yeah, that is what I understand. So it doesn't, I mean, yeah, so it will get the likelihood function, the likelihood distribution for each time point. Yeah.
Okay. Thank you.
Anybody took a longitudinal data analysis?
Well, I did.
Okay. Oh, you did. So how did you learn?
We used the MD pattern thing to show the data analysis, the pattern of it, but I don't think the data set he gave us was that many data points.
Okay.
So I was just curious, like when we present things, if you say we have a missing data, do I just give her overall like 20% of data is missing? I don't have to say 5% is missing time 1, 2% is missing time 2, stuff like that. That's just my curiosity of how to report it.
Okay. I will study, I will read some paper, and then I will get you the answer in the next class. Okay. Because I'm not 100% how the different time points are dealt in the longitudinal missing data analysis.
Okay.
Okay.
That's good. Thank you.
Okay, sounds good. All right.